All right, hoping everyone's vacation's going well. Figure if we're gonna teach you some stats, we might teach you a little bit about good music. That was Huey Lewis in the News. I Want a New Drug, which is going to be the topic of the two-sample t-test you're going to be looking at today. There's a couple of things I want to cover just before we get into the actual testing and the problem that we're going to look at. Hopefully you've gone and taken a look at section 11.2 in your book and you've looked at some of the formulas that we're going to be looking at today. We need to have a small discussion about those before we move on. Here's the first formula we need to look at, and it kind of looks like a bear. You can see it's a degrees of freedom formula, and this formula actually appears on page 659 of your book. So if you want to take a look at it, you can do some of the additional reading. And essentially, this is how you can calculate degrees of freedom in a two-proportion setting for a t-test. And it's a very accurate calculation. And in fact, this is the calculation that your calculator uses. So if you're going to be using your calculator at all, these are the calculator degrees of freedom. And one thing that I'll say is that your t-test statistic and the probability that match up with it need to match in degrees of freedom with what you're doing. So if you're going to be using your calculator, you must state the calculator degrees of freedom. I'm actually going to do the problem that we're doing today a different way, but I did want you to notice this formula. This is not a requirement of the College Board for the AP exam. You don't need to know this formula. Your calculator will spit out these degrees of freedom and you should know where they're coming from. So I highly suggest you look on page 659 for a little bit more of an explanation of this. The second formula that you need to be familiar with is the test statistic for T in the two population or two sample setting. And here it is, and it looks like every other test statistic we've dealt with this year. In your numerator, you have your difference of your sample means. So we have x bar 1 and x bar 2 being subtracted. What you don't see to the right, again, could be written as minus mu1 minus mu2. But under the assumption of the null hypothesis where the two means are equal, there's no need to write that. And in the denominator, hopefully you see something from our random variable chapters early on, and that is a sum of standard deviations, but by way of variances, that we want to combine the two sample standard deviations, but we can't simply add those together. So we're squaring each one and then adding them together and taking the square root based off of their respective sample sizes, n1 and n2. So this is our t-test statistic that we're going to be using today. My suggestion at this point is to probably pause the video and take a good read through this and try to have a general understanding about what I'm going to talk about. But this is going to be the two-sample t-test. So go ahead and read about the medication being administered to lower blood cholesterol. All right, just to organize our thoughts real quick, I think it's best that we probably write some things down here so that we're all consistent with them throughout the rest of the problem. So I'm really looking at two groups or samples, or two populations really. So group 1, or if you want to call this population 1. I'm going to call population 1 the standard drug group. So these are the people that are taking the old drug. And we know that there are 50 of them. In fact, this works out well that there's 50 in each group. I'm going to say that x bar 1 is going to equal 10 milligrams per deciliter, which is the decrease. And even though it's a decrease, I don't need to write it as a negative 10. I'm looking at decrease as a positive number, the bigger decrease being the bigger positive number. And then my standard deviation, so I'm going to call it S1, is 8 milligrams per deciliter for population 1. Group 2, or population 2, is going to be the new drug group. Hence Huey Lewis's I Want a New Drug. So this is new drug. And again, the statistic x bar sub 2 is the 18 milligrams per deciliter. And S2 is going to be 12 milligrams per deciliter. And you might be looking at this right now and saying, well, clearly, I mean, a decrease of 18 versus 10, it's going to be significant. But one of the things that I would also point out is taking a look at the standard deviations and seeing that there is actually more deviation in this group. So numbers are going to be a little bit more all over the place. So maybe you have some really high numbers and some really low numbers as well. Whereas up here it's only 8 for this group. So maybe we'll be shocked at what we see, maybe we won't. Let's go check it out. The other thing that I want to do is just define right here for you. Why don't we take a look at this at alpha equals 0.05, kind of our standard that we always do. So that's where we're going to go on to the next page. All right, I've taken the liberty of writing down the null hypothesis for you. Under the 2-sample setting, we're going to always have that mu1 equals mu2, that the true mean in this case of the standard drug group's cholesterol level is equal to that of the decrease in the new drug group's cholesterol level. Our alternative hypothesis, we're trying to see whether or not the decrease in the new drug group is more significant. So we're actually going to have mu1 less than mu2, and that being that there's a bigger decrease in the new drug group, so mu2 being greater than mu1. You'll see in the book there are some alternate ways of writing these null hypotheses. You could take your HO and say that mu1 minus mu2 is equal to 0, that the difference between them is equal to 0, and then if we wanted the equivalent alternative for that, we would be looking at what happens when we compare mu1 minus mu2. And in this case, if we think that mu2 is going to be a larger decrease, this would actually come back at less than 0, because mu2 being a bigger number would produce a negative number when the subtraction happens. So that would be an equivalent way of writing it. So you'll see that in the book, and feel free to use that if you want to, and then just have the appropriate words to match up with that. So making sure to not forget about the alternative, I'll write it down here. The true mean decrease in the standard group is less than that of the new drug group. I'll put an exclamation mark because that's a lot of words. All right, so we have our null and alternative defined. Let's go look at the conditions. The 4 conditional checks for the 2-sample t-test revolve around the things that we've been talking about all year. So simple random samples. Again, we want 2 sets of random samples if possible when dealing with 2 populations. To use the t-distribution, are we normal enough to do so? Do we have the criteria met so that there is not an overabundance of error in the tails of the distribution? Do we have independent populations? We want to make sure that we're sampling out of 2 different populations and there's no overlap. And finally, is n greater than or equal to 10n? Is it appropriate to use things like the standard error calculation as an estimate, or does that fail based on the sample sizes? So in this particular case, although we don't have random samples, we're running an experiment. It's really hard to go out to the public and pluck people off the street and start administering drug treatments to them. So in this case, in the experimental setting, the randomness occurs with the random assignment to treatments. So it said in the problem that the two groups were randomly assigned 50 and 50. So we have random assignment of treatments. So that is good enough for us in terms of a simple random sample. For normality, again, being normal enough to use the t-distributions, in both cases, n1 is equal to 50 and n2 is equal to 50. We don't have anything that we can graph. We have no information about the normality of these, but we do know that they are both greater than or equal to 30. So by the central limit theorem, we can say that these are going to be approximately normal. So once again, a check on that condition. For independent populations, again, we're talking overlap. It's not possible for someone to be in both the new drug treatment group and the standard drug treatment group. So it's really impossible to be in both groups. And that's really what we're concerned with here with independence. And then population size. In this case, is n greater than or equal to 50 times 10 or 500, and we would want that for n1 and n2. Again, both of these being 50. And I think that it would be safe to assume that probably people with that qualify to take the drug having this overabundance of cholesterol is probably greater than or equal to 500. So both of these conditions would be met. So on all accounts in this particular setting, we do have the conditions met to go ahead and use the t-test statistic and calculate a p-value. Now is the easy part, time to just plug some numbers in and generate a value. So I'm going to go ahead and throw in my x bar 1 number, which was 10 minus 18 all over the square root. And then we have an 8 squared over 50 plus a 12 squared over 50. So that's going to generate my t-test statistic. And when you plug that in your calculator and do the math out, you get a negative 3.9223. And, that's a pretty large t-value in terms of distance from 0, so that may lead us to already start believing that we have some significant results here. One of the things that I have to point out is I am doing this at what we call the conservative degrees of freedom. The conservative degrees of freedom says just look at the 2 sample sizes, take the smaller of the 2 sample sizes, and subtract 1 from it. It's very conservative. It's saying worst case scenario, this would be the p-value associated with this t-test statistic. So for this particular setting, I'm going to say that I'm doing this at 49 degrees of freedom. I'll talk a little bit more about what the calculator does towards the end of the slides. So in terms of generating a probability statement, I'm looking for what's the likelihood that t is less than or equal to negative 3.9223. We can get that by using TCDF. Lower bound negative 1E99, upper bound negative 3.9223, degrees of freedom 49. And of course I'm going to come through and label these lower bound, upper bound, degrees of freedom. And when you plug that in your calculator, we find that the probability of t less than or equal to negative 3.9223 is approximately 1.3652 times 10 to the negative 4. Yep, that's pretty small. So what we thought from the beginning is actually shown here with the very negative t-score and the p-value of 1.36 times 10 to the negative 4. All right, so our conclusion is here. Again, in context relating back to the null and alternative hypotheses, because our p-value of 1.3652 times 10 to the negative 4 is definitely less than alpha, 0.05. We're going to go ahead and reject the null hypothesis, which was that the two means were equal in favor of the alternative, that the true mean decrease in blood cholesterol of the new drug is significantly more than that of the standard drug group. And again, based on our X bar value, based on our sample sizes of 50, we do have some convincing evidence here that our sample data suggests that the new drug group is going to show a greater decrease in blood cholesterol. We're not 100% sure. Again, statistics never allow us to say that we're 100% sure, but with such a low p-value, we have some significant evidence in favor of that alternative hypothesis. On the next slide, I just want to show you what was going to happen if you went ahead and used your calculator for this, and show you how those numbers differ slightly from what we have here. All right, what you have here are the screenshots from your calculator that you would see if you did run a 2-sample t-test. So in the stat test menu, you're going to be going down to number 4, which is the 2-sample t-test. And because we are entering in statistics and not data, I've highlighted statistics and entered in my sample means, my sample standard deviations, and my sample sizes for both group 1 and group 2. This third screen over here just kind of is the scroll down of it, where I have chosen my alternative of mu1 less than mu2. And in terms of pooling, there's a no here. It got blocked out when the cursor was on it. The question here is, are the standard deviations for the two groups similar enough to say that we can pool them into one large group? And really what that's going to require is some analysis of variance, which we're not doing at this point. So we're going to answer no to that question at all times. We'll leave it toggled on no. We should never really choose yes. So, you know, stay away from the old pool. It's not necessarily safe. That's different than the pooled p-value, p-hat from the last chapter, so it's not the same type of thing. The fourth screen down here shows you the results of running the two-sample t-test. Again, same t-value, but different p-value in this case. P-value being 8.8 times 10 to the negative 5, so a factor of 10 smaller, and that is due in part to the degrees of freedom. And this goes back to that formula from page 369 that we were talking about earlier in the video, that this is the very accurate degrees of freedom, not the conservative degrees of freedom. So we've actually, you know, taken the curve and put less error into its tails, therefore decreasing the probabilities in the tails. So when we're looking at negative infinity up to negative 3.9 for our t-distribution, there's now less area in the tails because we've gone from a 49 degree of freedom t-distribution to an 85 degree of freedom t-distribution. Again, what do you need to see? You need to see agreement in your probability statement with the degrees of freedom. Using the conservative degrees of freedom, we had a different p-value, and that needed to match the 49 degrees of freedom. If you're going to use your calculator for this type of problem and report the p-value at 8.8 times 10 to the negative 5, you have to make sure that you're reporting 85.37 degrees of freedom. If you reported 49 degrees of freedom with this p-value, you would get knocked for that. There needs to be agreement between your p-value and the degrees of freedom that you used. All right, so keep these things in mind. Again, don't forget to comment on the Edmodo post about the video. Have a great rest of your vacation. We'll see you when we get back.